All right, so by definition, the unit circle is a circle with radius 1 and center at the origin. The equation of the unit circle is x squared plus y squared equals 1. So let's graph the unit circle along with one of the special triangles from 7.1. We'll use the pi over 6, pi over 3 right triangle, which is also the 30, 60, 90 right triangle, with the angle pi over 6 in standard position. So in this diagram, we have that this vertex for the angle pi over 6 is located at the origin, so at 0, 0. And we're on a unit circle, so that indicates that the hypotenuse of every triangle whose hypotenuse lies on the unit circle will always have radius 1. So if we wanted to start talking about our trigonometric functions, our point P of xy would correspond to, well, the side length here would be x, and the vertical side length would be y, because to get to the point P on the unit circle, it would have coordinate x, y. So I'd have to go x units right in this diagram and y units up. So then we can start talking about our trigonometric functions. So we know that the point PY, if we're at the angle pi over 6, this was one of our special triangles. So we know that this is going to be, if we looked at our diagram, we have this triangle right here. It's laying on its side. But there's something else we're going to have to take into account. So we've got this triangle. Right here. And we notice something. The hypotenuse of this triangle is 2, but since we're on the unit circle, what's the hypotenuse of the triangle in question? Well, it has to be 1. But the triangles have all three same angles. So the triangles are similar by angle, angle, angle. So that means that the proportion of their sides must be equal. Well, that means that my proportionality for each of these, my k, has to be 1/2, because 2 times 1/2 gives me 1. So that would make my other sides equal to 1/2, and this side would have to be equal to root 3 over 2. And we'll notice, as we talked about in the previous section, that the trigonometric ratios for similar triangles is always equal. So in terms of this then, we'll notice if we wanted to start talking about our trigonometric ratios, since we're on a unit circle and our hypotenuse is 1, normally sine theta is the opposite of theta over the hypotenuse. But on the unit circle, we know that the hypotenuse is equal to 1. So then the opposite of our angle theta then would be y, which then just simplifies to y. So on the unit circle, sine theta is just the same as the y coordinate. Using some similar reasoning, if we go to cosine theta, that's adjacent theta, once again over our hypotenuse. And the hypotenuse is still 1. And adjacent is going to be x. But x divided by 1 is just x. So the key idea here is, since the ratios of similar triangles trigonometric functions are always equal, on the unit circle, we can simplify the definition of sine and cosine. Since the hypotenuse is 1, anything divided by 1 is always itself. So on the unit circle, we have sine theta equals y, and cosine theta equals x. So and then combining those, we also know that tangent theta is equal to sine theta over cosine theta, which would then be y divided by x. We could also relate that to all of our reciprocal identities as well. So if we take these facts about sine and cosine on the unit circle and combine them with the equation of the unit circle, we're going to get our first not necessarily our first, but the first Pythagorean identity. So basically what we just said is that cosine theta is x over r, and sine theta is y over r, but on the unit circle, r is 1. So we get x is cosine theta and y is sine theta. Using the fact that the equation of the unit circle is x squared plus y squared equals 1, because that's the equation of a circle with center 0, 0 and radius 1, gives us the first Pythagorean identity. So if I replace x with cosine and I replace y with sine, it gives me cosine squared theta plus sine squared theta is equal to 1. And this brings us to our next convention, which is for trigonometric functions, we're going to write our exponents in a slightly different location. So for trigonometric functions, we will write the exponent between the function and its argument. We will write cosine squared theta instead of the version with tons of parentheses or even without, or cosine theta without the parentheses. So note, we need to be careful that cosine squared of theta is not the same thing as cosine squared of theta. So cosine theta squared tells us square theta, and then find the cosine. Cosine squared theta tells us find the cosine and then square it. So with trigonometric functions, we're going to write our exponent between the trigonometric function and the argument of the trigonometric function. So the other thing is we will never use exponents on trigonometric functions. So what I mean by that is we're not going to write cosine with a power of -1 to mean 1 over the cosine of x, because normally a negative exponent tells us to move something from the numerator or to the denominator. So we'll talk about what this means in detail later. This means the inverse of cosine. So I mention that because on our calculator, if you look at sine, cosine, and tangent, all the secondary functions have the -1. That does not mean the reciprocal identities. So sine to the -1 is not the cosecant function. Cosine to the -1 is not the secant function. So we have symbols for that. 1 over cosine is really secant x. All right, so an angle theta corresponds to the point -√2 over 2 and -√2 over 2 on the unit circle. Find the sine of theta and find the cosine of theta. So let's go ahead and draw a sketch of our unit circle. And we're talking about the point -√2 and -√2, so these are x and y coordinates. So both x and y are negative, so x and y are negative down here in quadrant number 3. So I'd have -√2 over 2 and -√2 over 2. And that gives us this. So our angle has its initial side, the positive x-axis, and goes to here. So this would be my angle. Theta would be the rotation from the positive x-axis to that terminal side whose point lies on the unit circle at -√2 over 2 and -√2 over 2. Okay, so we've got this triangle there. And let's go ahead and zoom in on it a little bit. So then if I were to drop a perpendicular to this point right here, I can figure out my coordinates. So here's my coordinate out here, -√2 over 2 and -√2 over 2. So that's my xy coordinate down here in quadrant 3. So then that would make each of these sides -√2 over 2 and -√2 over 2. So if I want to find the sine of this angle, I would need to know my hypotenuse while I'm on the unit circle, so it's 1. And so by definition, sine theta is just going to be the y value, right? So it's -√2 over 2. And cosine theta would be the x value, which is -√2 over 2. So let's talk a little bit about this. Did I need to draw any of those pictures? Not really, because it helped me visualize it. But what was our definition of sine and cosine on the unit circle? Well, on the unit circle, cosine is x and sine is y. Well, what's my x coordinate and what's my y coordinate? X was -√2 over 2. Oh, y was -√2 over 2. So what was sine and cosine? The x and y coordinate. That's why the unit circle is very helpful, is to find the values of sine and cosine. If we know we're on the unit circle, it's just the x and y coordinate of the point on the unit circle on the terminal side. All right, so let's draw ourselves another diagram this time. So we want to find the sine of 0, pi over 2, pi, and 3 pi over 2. So I draw my sketch again, and this time I was given angles and not points. Okay, to help us, well, 0 here, since we did not write the degree sign, all of these are measured in radians. So the entire circle is 2 pi radians, right? Well, so 0 is going to correspond to this point right here. So if this is 0, what's its ordered pair going to be if it's on the unit circle? Well, my radius is 1, so that's going to be at the point 0, 0. If I go with pi over 2, well, how many degrees is pi over 2 going to be the same as? Well, pi over 2, if we take our proportion to the whole circle, it would be pi over 2 divided by 2 pi over 1 is pi over 2 times 1 over 2 pi. Our pi's reduce out, and we get 1 over 4. So it tells us that it is 1/4 of the way around the circle. Well, 1/4 of the way around the circle is going to be right here. And what is the coordinate of that point? Well, it's going to be 0, 1. Similarly, pi, well, pi is half of 2 pi, so that's going to be halfway around the circle, or 180 degrees. I shouldn't use red, though, because I made my circle red. Purple. So pi is going to be halfway around the circle, so that's going to be at this point, -1 and 0. And then lastly, we have 3 pi over 2. If we converted that to degrees, we would get 270, or its proportion would be 3/4 of the way around the circle. So 1/4, 2/4, 3/4. It's going to be down here at 0, -1. So by definition, we know sine of our angle is equal to y. So the sine of 0 is going to be the y-coordinate, and the y-coordinate is, at this point, 1, 0 is 0. And if we try the sine of pi over 2, we go to our pi over 2, or our 90 degrees, and sine is the y value, so our y value at that point is 1. So the sine of pi over 2 is 1. If we want to calculate the sine of pi, we determined pi was halfway around the unit circle, so that was going to be here. So our y value here is once again 0. So the sine of pi is 0. And lastly, we want to do the sine of 3 pi divided by 2. So we look at our y value up here, and we get our y value is -1. So the sine of 3 pi divided by 2 is -1. So knowing that sine is y, we can find the points that correspond to the angles on the unit circle and then read off the y-coordinates. So as a bonus, we weren't asked this, but then what's the cosine of 0 going to be? Well, cosine is x, so cosine of 0 would be 1. The cosine of pi over 2 is going to be our x-coordinate up here. So in orange, our x-coordinate was 0. The cosine of pi is going to be the x-coordinate halfway around the circle. So that's going to be negative 1. And then lastly, if we did the cosine of 3 pi over 2, well, that's 3/4 of the way around the circle. That's here in green. And our x-coordinate in green is 0. All right. Our next example says if cosine theta is negative 3/7 and is in quadrant 3, find the sine of theta. So we start by drawing our diagram. So quadrant 3 is down here. So we have our unit circle. Looks something like this. We have our quadrant 3 is down here. We know our radius is 1. But then we have cosine. And this time we don't actually know our radius is 1 when it comes to this diagram. So we have cosine theta equals negative 3/7. But we also know the cosine of theta is equal to adjacent over hypotenuse. So then that informs us that the adjacent side must measure 3 and that the hypotenuse must measure 7. So on this circle, we're going to have that this side, the hypotenuse, is going to have measure 7, and the adjacent side is going to have measure 3. So it's worth noting the 3 must be negative. So the reason that the 3 must be negative is in quadrant 3, both x and y have to be negative. The hypotenuse can never be negative. So then we have this side is 3, and we need to find the missing side over here. Well, we want this, which we're going to call y. So by the Pythagorean theorem, we know that negative 3 squared plus y squared has to equal to 7 squared. So negative 3 squared plus y squared has to equal to 7 squared. That gives us 9 plus y squared is equal to 49. Minus 9, minus 9. So y squared is equal to 40. And we get y equals plus or minus the square root of 40. And it's worth noting 40 is equal to 4 times 10. So the square root of 40 is the same as 2 times the square root of 10. So plus or minus 2 square roots of 10. We have the plus or minus, but we choose the negative because y is negative in quadrant 3. So we choose the negative square root because y is negative in quadrant 3. So we select this, and that tells us that we have negative 2 square roots of 10. Well, if that's the case, we want to know, well, what is the sine of theta? Well, sine theta is opposite over hypotenuse. So our sine is going to be negative 2 square roots of 10 over our hypotenuse, in this case, which was 7. So that method, we drew our triangle, and we knew that it had to be a right triangle, so we then used the Pythagorean identity to solve for the missing side, and then used our definition that sine was opposite over adjacent. There is another method we could have used. And that one is the first Pythagorean identity. The first Pythagorean identity says sine squared theta plus cosine squared theta has to equal to 1. We know that our theta by hypotenuse, or by hypothesis, was in quadrant 3, and we know that cosine is negative 3/7. So we know cosine theta is negative 3/7, and theta is in quadrant 3. So then that would give us sine squared theta plus our cosine squared theta is negative 3/7 squared is equal to 1. So then we would have that sine squared theta plus negative 7/3 times negative 7/3, 3 times 3 is 9, 7 times 7 is 49, is equal to 1. So we then subtract 9 over the square, or 9 over 49 from both sides. So this gives us 1 over 1 is the same as 49 over 49. So 49 over 49, take away 9 over 49, gives us sine squared theta is equal to, well, 49 take away 9 is 40 over 49. We take our square root, and we get sine theta is equal to plus or minus the square root of 40 over the square root of 49 is 7, not 9. And as we saw above, the square root of 40 simplifies into 2 square roots of 10 over 7. So we get that same number, but once again, since we are in quadrant 3, y must be negative. So we select just the negative square root, and we get the answer negative 2 times the square root of 10 over 7. So either way, we get the same correct answer. But they're really the same method, because where did the first Pythagorean identity come from? Well, the first Pythagorean identity was the equation of the unit circle, which is really just the Pythagorean identity a squared plus b squared equals c squared, with c equal 1. So in essence, they are really the same thing. So we wish to find the value of sine and cosine for the following angles. All right, so let's go back to the very first page in our handout, which is our good friend, the unit circle. So, as we've been talking about, on the unit circle, what do we know about sine and what do we know about cosine? Well, sine is y and cosine is going to be x. So, we take our angles, we have 0, pi over 6, pi over 4, pi over 3, and pi over 2. And we'll note that these are the same as 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. So we look at our unit circle. If we want to know what the sine of 0 degrees is, that's on the positive x-axis, so we go out here, and we know that sine is y and cosine is x. So our y-coordinate is 0, so the sine of 0 is 0, and our x-coordinate is 1, so the cosine of 0 is going to be 1. We go to 30 degrees, or pi over 6 radians. That's along this line, and we have our x and our y. So our sine is going to be 1/2, and our cosine is going to be the square root of 3 over 2. We do the same thing moving along our line of 45 degrees, or pi over 4. And here we notice x and y are the same, both of them being root 2 over 2 and root 2 over 2. We get to our next one, which is 60 degrees. So that's going to be here, or pi over 3 radians. So our x value is going to be root 3 divided by 2, and our y value is going to be 1/2. And then lastly, going straight up, we get a right or 90-degree angle, or pi over 2 radians, and our y value here is going to be 1, and our x value is going to be 0. So that first page, the unit circle takes into account quadrants, because it will have the signs of each of these, and on the unit circle, they draw only the hypotenuse, where the x and the y are really these sides of the triangle. But it would be very much too busy if we drew every single triangle on the unit circle. It just gets too busy to look at. So we draw only the hypotenuse, and then we put the lengths of the sides, which are the coordinates, out here on our unit circle. So essentially, the unit circle is just this diagram, but everything's already filled out for you. So then we want to know what sine is, we get the y-coordinate. If we want to know what cosine is, we grab the x-coordinate. If we want to know what tangent is, we would take y divided by x. So all of that information is encoded in our unit circle. And we also note that at complementary angles, so 30 and 60 degrees, our complementary angles are pi over 6 and pi over 3, our trig functions have the same values. 0 is complementary to 90 degrees. Pi over 4 is complementary to pi over 4. 60 is complementary to 30, and 90 is complementary to, right? So we have that relationship between complementary angles and their corresponding co-functions, right? So the co-functions are equal to each other at the complementary values, aka that's where the co comes from in co-function. And that's the manifestation of our co-function identities. All right, so let's take a look at our next example, which is we want to use our calculator to find some of these values. So as we noted, we need to be careful with the mode on our calculator. So first thing we want to note is the following. 30 degrees is the same as pi over 6 radians, right? So those are actually the same angle. So if we do this correctly, we should get the same value for sine of 30 degrees as we do for the sine of pi over 6 radians. So we grab our calculator, and by default, what mode is our calculator in? So if we press our mode key, unless we've changed it, by default our calculator is in radian mode. So I've switched my calculator to degree mode. So let's go calculate the sine of 30 degrees. And I get 0.5, or as a fraction I get a half. So the sine of 30 degrees is equal to 1/2. If I just try to directly take the sine of pi divided by 6, I'm going to get this, which is not the correct answer, because pi over 6 is measured in radians. So I convert back into radian mode by pressing mode, going down to radians, changing to radians, and now if I take the sine of pi over 6, which we know pi over 6 radians is the same as 30 degrees, we get the same value that we got when we did just the sine of 30 degrees. So this one is incorrect. It's in degree mode. This one is our correct answer. So the sine of pi over 6 is 0.5, which is the same as 1/2. And since 30 degrees is the same as pi over 6, they should indeed have the same value at those points. So the biggest thing we need to be careful with is to keep our calculator in the proper mode. So something I personally like to do, and it's completely up to you, since we will work a lot with radians, and in your next math class, when you take calculus, degrees kind of go the way of the dodo. Advanced mathematics uses almost exclusively radians. I prefer to keep my calculator in radian mode. So instead of having to go in and change it every time, if I just want to calculate the sine of 30 degrees, I go sine 30, and then if you look on your apps key, so in the third row, second column, the secondary function on your calculator says angle. So if we go to there, you'll notice it has a degree symbol. This will override the mode that your calculator is in. So if I go 30 and insert the degree symbol, my calculator knows, even if it's in radian mode, that I want degrees. So you can go in and just do one-offs and say, all right, this time it's in degrees, so give me the degree measure. I find that more convenient than having to bounce back and forth between the two different modes. Because my problem is if I'm bouncing back and forth, I always have to go in there anyway because I never remember which mode it was in last time I used my calculator. So if I just pick one and leave it, aka radians, I can then use degrees whenever I need to by going to the degree menu. So this is just a suggestion. If you want to switch it every time, go for it. There is nothing wrong with that. You will get the same answer either way. It's just a different method to accomplish the same thing. All right. So it's now your turn. I would like you guys to find the cosine of 15 degrees and the cosine of 5 pi over 6. Is that 15 degrees and 5 pi over 6 are actually the same angle, right? So if we wished to convert 15 degrees into radians, so 15 degrees, our conversion factor from degrees to radians was pi radians over 180 degrees. Our degrees reduce out, and that gives us 15 pi over 180, and 15, oh, just kidding, these are complementary angles. So 15 goes into 180, times, guess they're neither. So 15 degrees would be pi over 12 radians if you were interested. So let's go ahead and calculate each of these. So the cosine of 15 degrees gives us this value, and we'll note that it would be the same as if I did pi divided by 12. So that's our first one. So the cosine of 15 is approximately, or of 15 degrees is approximately 0.965 ... And then the cosine of 5 pi over 6, so we go cosine 5 pi and divide that by 6. We get negative 0.88, and that makes sense because 5 pi over 6 is bigger than pi over 2, but less than pi, so 5 pi over 6 is in quadrant 2, and cosine is x, and the x coordinate is negative in quadrant 2. All right. So using the unit circle as the basis for the domain yields a domain of all real numbers for each trigonometric function. So notice that the domain is all real numbers and not angles. So why is that? Well, it's because how we've defined theta. Theta was x divided by r when it's in radians. So if this has units length and this has units length, the units reduce out and we just get a pure number. So there are no units attached to the input of a trigonometric function in radians. So it's a pure number. So our domain can be extended then to all real numbers. And the range for each function is -1 to 1. Well, why would the range of each of the trigonometric functions be from -1 to 1? Well, that comes back to our unit circle. Well, what is the biggest x value on the unit circle? Well, that would be over here. And as we saw in this example, the biggest x value on the unit circle is +1. The smallest x value on the unit circle is -1. The biggest y value on the unit circle is +1, and the smallest x value on the unit circle is -1. So that's why our range has to be from -1 to 1. It's our x max and x min on the unit circle, and our y max and our y min on the unit circle. All right, so our next definition is reference angles. So the reference triangle will always have one leg on the x-axis, and the other leg will be parallel to the y-axis. The reference angle is always a positive angle between 0 and 90 degrees, or 0 and pi over 2 radians. The angle is measured from the x-axis to the hypotenuse of the reference triangle. Let's look at a few examples. So in quadrant 1, it's just the same triangle that we've been using the entire time. Our x-axis side is in orange, our y-axis side is in red, and our hypotenuse. So our reference angle would be the same as the angle rotated from the positive x-axis. So in quadrant 2 over here, if this is our angle theta, in quadrant 2, theta is less than pi, but greater than pi over 2, or the same thing, it's bigger than 90 degrees, but less than 180 degrees. So that's our angle theta. The reference angle is always the angle measured from the positive, or from the x-axis to the hypotenuse. So in this example, theta and alpha would be supplementary angles, because if you added them up, they would give you 180 degrees, or pi radians. So in quadrant 1, the reference angle is the same as theta. So in quadrant 1, theta and alpha are the same. Quadrant 2, they are complementary or supplementary. So now let's take a look in quadrants 3 and 4. So in quadrant 3 down here, we have theta is our angle, and our reference angle is always measured from the x-axis to the hypotenuse. So our reference angle here is going to be what? Well, it would be theta take away 180, or theta take away pi. In our last quadrant here, theta is all the way around, and our reference angle goes from the x-axis to the hypotenuse, and that's here. So our reference angle here would be what? All right, so let's come up with some explicit formulas for each of these. So in quadrant 1, theta and the reference angle are equal. So in quadrant 1, theta and the reference angle are equal. Well, how would we compute alpha in quadrant 2? Well, we know the two angles are supplementary, which means their sum has to add up to 180. So here, alpha would be equal to pi radians take away theta, or 180 degrees take away theta. In quadrant 3, our reference angle is the angle as measured from the negative x-axis to the hypotenuse. So theta is all the way to here, and our reference angle is only from here to here. So the part that we don't want is this. Well, that's pi, or 180 degrees. So in quadrant 3, alpha is equal to theta minus pi, or theta minus 180 degrees. Lastly, in quadrant 4, alpha plus theta has to equal 360 degrees. So alpha would be what? So if alpha plus theta equals 360 degrees, or 2 pi radians, then alpha would have to be 2 pi take away theta, or 360 degrees take away theta. Because if you add them together, you would have to get one rotation around the entire circle. So I would strongly recommend that you just get comfortable with drawing the pictures and don't try to memorize these 4 formulas. You can do it that way, it's terrible, but it's a lot easier to just get comfortable with drawing the pictures and reason through what it has to be based on where it's located. Because we know as we go around our unit circle, up is pi over 2, or 90 degrees. This is pi, or 180 degrees. This is 3 pi over 2, or 270 degrees. And then this is either 0 and 0, or 2 pi and 360, depending on what you're trying to do. And we can figure out what our angle has to be based on its location, but if you want, you can memorize or add those formulas to your note sheet. At the end of the day, you will get the same answer regardless. All right, example 6, use reference angles to find the cosine of 5 pi over 3. So 5 pi divided by 3, that's going to be in quadrant 4. So in terms of our picture, since we're in quadrant 4, we know that this angle is 5 pi over 3. So then our reference angle is whatever is left to get all the way around. So that's going to be pi over 3. And we can check using our formula. Alpha would equal to 2 pi take away 5 pi over 3. So getting a common denominator, we'd have to multiply the top and the bottom by 6, or by 3 to get 6. And that would give us 6 pi over 3 minus 5 pi over 3. And 6 pi take away 5 pi is going to be 1 pi, or just pi over 3, which is indeed what we got for our reference angle. So then in quadrant 4, y is negative and x is positive. So since cosine is x, it will be positive. So then we've got our triangle down here. And our reference angle is pi over 3. So if we go back to our special triangles, we've got a pi over 3, that's this one. So pi over 3, pi over 6, 90 triangle. So pi over 3 goes with the side 1, and pi over 6 is going to go with the side square root of 3. So 1, that's going to be pi over 6, that's going to be square root of 3, and the hypotenuse is 2. So then cosine of 5 pi over 3 is going to be equal to the value from our reference triangle. And since cosine is x, we know it's going to be positive, and cosine is adjacent over hypotenuse, so we get 1/2. Adjacent over hypotenuse. So if we wanted to be technical, since we are in quadrant 4 and y is negative, that side of the triangle is technically negative square root of 3. And if you took the sine, y is negative in quadrant 4, and you would get a negative ratio, as you should. All right, it's now your turn. All right, so once again, this thing's going to be down here in quadrant 4. So we're at 11 pi over 6, which means that angle is 11 pi over 6. So then alpha, our reference angle, this needs to add to 2 pi, would just be pi over 6, or doing the formal computation, 2 pi minus 11 pi over 6 indeed gives us pi over 6. So now we want to find our coordinates out here on our unit circle. So our point P, x, y. Once again, we're in quadrant 4, so y is negative and x is positive. So x is positive and y is negative. So then, using our same reference triangle that we used above, we have our, once again, our 30, 60, 90 right triangle. So pi over 6, pi over 3, and 90. So that's going to be our 1, 2, square root of 3. So x is going to be our cosine. So our cosine of pi over 6 is going to be root 3 over 2. And the sine of pi over 6 is going to be 1/2. But we're in quadrant 4. So y is negative. So we get this value. And we get root 3 over 2 and negative 1/2. So the point on our unit circle would be root 3 over 2 and negative 1/2. All right, so the reference angle allows us to use the two special triangles that we learned at the very, very beginning. If you know those two triangles and the values on the axes, you can figure out every value on the unit circle without having to memorize the unit circle. I know for a lot of people, they're just taught to memorize the unit circle, but you really only need to know two triangles. And that gives you all of the information as long as you figure out which quadrant that reference triangle belongs in. All right.